Okay, so welcome back, everybody. All right, so before I get back into what we were going to do yesterday with integrating factors, I want to do one more example of exact differential form stuff. So here's one more example. So let's say I'm asked to find an implicit general solution to the equation x squared cosine x e to the y plus 2x sine x e to the y. The argument of cosine and sine is just the x here, so maybe I should write that. Okay, plus e to the x cosine y. All that is one piece here, dx, plus x squared sine x e to the y minus e to the x sine y dy is equal to 0. Okay, so here's my equation. Okay, so this is pretty long, right? This looks like it could be almost undoable, but let's see here. This is my m, right? And this is my n. And so no matter how this thing looks, my approach here is to always check exactness first, because this is going to tell me what I have to do, right? And we'll see what we have to do if this thing is not exact. Let's check exactness real quick. So um, if I check this, I'm checking that the y partial of m is equal to the x partial of n. So what's the y partial of m? Let's just go term by term. So y partial of m, all the things that depend on x are treated as constants. So e to the y is the only thing I'm taking the derivative of here. So this is just x squared cosine x e to the y. Okay. Plus the next thing, again, all this x stuff is treated as constant, and the only thing I'm taking derivative of is e to the y, so this is just plus 2x sine x e to the y. Here, the only thing being taken, having its derivative taken, is this cosine y, and the derivative of cosine y is minus sine y, so this is minus e to the x sine y. Okay, so that's the y partial of m. All right, so what's the x partial of n? So the x partial of n. All right, let's see. So there's two terms here. There's a product in x here, so I'm going to have to use the product rule. So let's do that. Let's use the product rule here. Remember, this e to the y multiplies both of them, so that is not included in the product rule, right? Because that doesn't depend on x. And so then it's this x squared sine x term that matters. So the derivative of x squared sine x, that's 2x sine x e to the y, plus x squared times the derivative of sine x, which is cosine x, so plus x squared cosine x e to the y. And the derivative of minus e to the x sine y with respect to x is just minus e to the x sine y. Those match up, those match up, those match up. These are actually the same thing, right? So it didn't look like, maybe just glancing at it at first, it didn't really seem like it would be exact. They maybe didn't seem like it would work out exactly, but that's why you have to actually check, because you know, here we have that actually this works out perfectly. So this is going to be an example of a nice one, even if it looks kind of involved. This is actually going to be one of our nice examples. Okay, so then what does this mean? So then I have thus I seek h of xy such that the x partial of h is equal to m, right? X squared cosine x e to the y plus 2x sine x e to the y plus e to the x cosine y. And the y partial of h is x squared sine x e to the y minus e to the x sine y. Okay. So, there's what we end up with. Now, what do we do next? I look at these and I ask myself, like, which one do I want to start integrating, right? Now, I told you it doesn't really matter necessarily. Like, we know that we have to use both equations, so it doesn't really matter. But functionally, right, like if you're taking an exam, doing homework, going through a quiz, you should want to pick the thing that that you know how to do, that you know how to integrate. Okay, so technically you could use either thing here, but it's a lot easier. If I integrate this with respect to x, look at the integrals I get. I get the integral of x squared cosine x e to the y plus 2x, or plus the integral of 2x sine x e to the y plus the integral of e to the x cosine y. Those are terrible integrals to do. They can be done, of course, but it's easier to see how to integrate this second equation with respect to y, because both of the things involved, there's no product of y's here, right? So I want to use the second equation. We'll use the first equation in a minute after we've done this integral. All right, so using the second equation, how does this help me? So I integrate both sides with respect to y here, and I get that h of xy is integrating this with respect to y. That's actually just x squared sine x e to the y. Okay, integrating this with respect to y is minus cosine y, so this is a plus e to the x cosine y. And then plus I have a constant of integration, but I'm integrating with respect to y, so that constant of integration is generically a function, little h of x. Hold on real quick, I have to break up a fight between my cats. I don't know if you could hear them, but I have to break them up or they'll get pretty loud because they're being mean to each other. Okay. All right. So, I want to take the x partial of this thing and say, oh, well, I know that the x partial of this h has to equal this thing in the first equation. So that's what I'm going to use here. So I'm going to do the thing that I always do. I have x squared cosine x e to the y plus 2x sine x e to the y plus e to the x cosine y. That is equal to the x partial of h. But if I actually take the x partial of h from this thing that I found, so let's do this. I'm going to have to use product rule here for this term. So what is this? This is 2x sine x e to the y plus x squared cosine x e to the y plus e to the x cosine y plus little h prime of x. Okay. Now, let's see what happens here. So 2x sine x e to the y, that cancels with the same term on the left-hand side. X squared cosine x e to the y, that also cancels with everything on the, or with the other term, the same term on the left-hand side. E to the x cosine y also cancels. Now, you might say, if you believe what I told you before, you would know that all of these had to cancel at this step. Why? Because all of these things involve both x and y. But I've told you that if the algebra, like if you've done everything correctly, then the algebra at this step should work out in such a way that whatever cancellation happens here, what you should end up with is an equation that only depends on x. Okay, in this case, right? If we'd done it the other direction, it should only depend on y. But since each term depends on both x and y, you should know that, if I'm going to not be a liar to you, then every single one of these terms has to cancel if you've done this properly. And it does. So, if we had ended up with terms here that only depended on x, then that wouldn't be the case. But here, since each of these terms depended on both x and y, we knew that it has to work out like this. So then little h prime of x is 0, and of course that means that little h of x is equal to a constant. And so, since this is a constant, I can absorb that on the right-hand side, and so an implicit general solution is given by h of xy is equal to constant, i.e. x squared sine x e to the y plus e to the x cosine y is equal to constant. Okay, you could use your favorite software package if you like to actually plot out what some sample curves or trajectories for such an equation would look like. We'll do that later. Or rather, if you want to see some samples of this stuff, you should look at the notes. There's some really, really nice pictures that have been rendered, a lot nicer than what I could sketch here. Okay. So that's that. So let me know if there's any questions on that in the comments. Okay, so now what? Getting back to, again, right? What if the equation is not exact? I.e., we go to check, and the y partial of m is just not equal to the x partial of n. So, as we saw yesterday, the idea is multiply by rho of xy. This gives me an equation rho xy mxy dx plus rho xy in xy dy is equal to 0. And the idea is I'm not just going to multiply by any function rho of x and y. I'm going to pick a function rho of xy that makes the resulting equation exact. The reason I can do this is because if I began with an equation m dx plus n dy is equal to 0, and I told myself, okay, I want to solve this thing. I want to find all solutions of this. Well, it turns out that the solution set, if you think of the solution set as being the set of all solutions to this equation, the solution set of this and this are actually the same. Okay, so these are the same, these share the same solution set. And so it doesn't matter whether I deal with this or whether I deal with this. If you like an analog of this, right, imagine you were looking you were considering all solutions to the following relation, right? Like 2x plus 3y is equal to 5, right? You know that's the equation of a line, okay? But, of course, if I just multiply both sides by something non-zero here, so if I multiply by like 10, and this becomes 20x plus 30y is equal to 50, both of these are the same equation, right? Like, so both of these have the exact same solution set. Well, it turns out, something similar is true multiplying through by this non-zero rho. Okay, so rho is not just going to be any function, of course. The idea is that to choose rho such that this is exact. So if we call this thing, maybe I'll use a different color here. So if I call this thing like my big M, and I call this thing my big N, then the idea is that the y partial of M is equal to the x partial of N. Now we saw yesterday that if you actually write out what this means that the y partial of rho M must be equal to the x partial of rho N. This is kind of the best way of remembering what it is that has to go on here. Using the product rule for partial derivatives, what do I get here? Oh, that pin's no good. What do I get here? I get that the... Oh, that one's no good either. Okay. I get that the y partial of rho times M plus rho times the y partial of M is equal to the x partial of rho times N plus rho times the x partial of N. So this is a more complicated expression that I get here. Okay. Rather than remembering this boxed thing, I think it's typically easier to remember this thing. Okay, because conceptually what it is you're trying to do is pretty obvious from this. You're just trying to make this multiplied equation be exact. Okay. Now, as I said, this is a first order PDE. Okay. So this is a first order PDE. This is an object we're not going to study in this course. So then how am I going to expect you to solve it? Well, I'm going to expect you to solve it by reducing it to an ODE. And the way you're going to do that is you're going to assume that the rho that you're seeking only depends on one variable. So here we assume rho of xy is actually rho of x, or rho of xy is equal to rho of y. So here's what you assume. Okay, now, as I mentioned yesterday, if you ask, like, how do I know which one to assume, right? Those are two very distinct choices. So how do I know which one to go with? You are going to go with the one that makes your life easier, okay? So, for instance, if you assume that it's purely a function of x, then the y partial of rho is going to be 0, so this term is going to go away. So if m is something nasty, and maybe n is a little less nasty, then you would want to zero out this term to make your life easy. Alternatively, right, if n is maybe nasty and m is less nasty, you would assume that that rho only depends on y here, so that this term would be zeroed out. Sometimes both m and n are about similar levels of complexity, and so in that case you have a choice, right? You just choose one of those things, whatever works. Usually it's going to be very obvious which one you should pick. Okay, and rather than write out the general form in both cases, so the textbook does this, the notes do this, I'm just going to work through some examples so you can see how this works. You don't need to remember the general form. I always just remember this fact here, and that derives, what's going on here with the boxed expression. And so from that you get the equation. In either case, this is the important bit. In either case, the resulting equation for rho is a first order linear equation. And so, doing these problems are going to be a really good way of practicing simultaneously how to solve these exact differential form type equations, and also how to solve first order linear equations, because if you actually need to find this integrating factor rho, you're going to have to solve a first order linear equation anyway. So it's basically a 2-in-1 type problem, so these are really convenient for you to practice your solving skills, because you're going to have to do both. Okay. The other thing is, now you see why it's clear that we're right in using this term integrating factor for rho because it solves a first order linear differential equation. So it is, we know that those solutions have this integrating factor form. And so oftentimes this rho is, very literally the integrating factor. Well, I mean, you'll see that that's always the case for this assumption that we've made. Okay. All right. So let's see how this works. Let's do an example. All right. So maybe I'll start on the next page so that I get plenty of space here. All right, so let's do an example. Find an implicit general solution to the equation. Let's see here. So 2e to the x plus y cubed dx plus 3y squared dy is equal to 0. Okay. All right. So here is my m. Here is my n. So first thing we do, as always, is check exactness, right? So the y partial of m, so y partial of 2e to the x is 0. Y partial of y cubed is 3y squared. And the x partial of n is, well, the x partial of 3y squared is 0. Right. And of course, 3y squared is not equal to 0, and thus this equation is not exact. Okay, so we cannot just straightforwardly do the things that we were trying to do before. Now, what if you didn't check? Right? What if you didn't check? What if you didn't check this exactness condition and you just went on your merry way trying to do what we had done before? It'd be impossible. So you would get to some algebraic statement and you just start going in circles. You'd either get to something stupid like 0 equals 0 or something like that, or you would start going in circles. You'd be unable to actually finish what it is you're doing, and that's just how it works. So always check exactness so that you don't waste too much time trying to do something that's impossible. So this is not exact. So then how do we proceed from here? Well, I want to seek this integrating factor, right? So I seek rho of xy such that rho xy times m dx plus rho xy n dy is equal to 0. Well, that's the easy part. I've just multiplied this equation, and the y partial of rho m is equal to the x partial of rho n. Now, just writing out what this is again, right? So this is the y partial of rho times m plus rho times the y partial of m, and that's equal to the x partial of rho times n plus rho times the x partial of n. So we look at our expression here. N is slightly nicer or simpler than m. So maybe we want m to go away here. So then what I do is I assume that rho of xy actually depends on x only. Okay, so if I've made that assumption, then what happens here to this equation? Well, the y partial of rho is going to go away, so that's going to get rid of this m term here. So let me do that here. So if that's the case, then the resulting equation is rho times the y partial of m is equal to the x partial of rho. But if x, or if rho is only a function of x, then this x partial of rho is actually the full derivative with respect to x of rho. So this is rho prime of x times n, or d rho dx if you like, but I'm just going to write it as rho prime. So it's rho prime times n plus rho times the x partial of n. Well, now it's time to actually compute these things. So the y partial of m is 3y squared. So that goes here. The x partial of n is 0, so this term goes away. And so what I am left with is the equation rho times 3y squared, which is the, so this is the y partial of m. So rho times 3y squared, and that is equal to rho prime of x times n, which is also 3y squared. I can divide both sides by 3y squared, and so I get the differential equation rho prime is equal to rho. Okay. So, in this case, right, I did, in fact, get a first-order linear equation. But my first-order linear equation is particularly simple, right? This is one that we solved on day one of class without knowing how to solve a general first-order differential equation, right? We know what this one is. So if we want a rho that only depends on x that satisfies the differential equation, rho prime is equal to rho. An easy choice here. So choose rho of x is equal to e to the x, right? Now, what if this equation was more complicated? What if it was a more complicated linear equation? Then you would use exactly what we did in section 2 of chapter 1, which is our recipe for the general solution to a first-order linear equation. Okay, but here we don't have to do that. We can just say this. And you might say, wait, isn't there usually an arbitrary constant here? Well, we are happy to find a single row, right, that makes this work. So we don't care, we're not trying to be general here, right? We're not really seeking a general solution. We're seeking any solution that makes this work that's non-trivial, right? So we're seeking any non-zero solution to this thing. So here we go. Rho of x is equal to e to the x. This works, okay? So what am I saying here? So then let me revisit this. i.e., and I'll verify this here in a second. If I multiply both sides by e to the x, so e to the x times here's the, just to remind you. So e to the x times 2e to the x plus y cubed dx plus 3y squared e to the x dy equals 0 should be exact. That's what I'm claiming here. So I take this equation, I multiply by rho, which is e to the x here. So this should be exact. So let me recalibrate here. Let me say, okay, here's my m, here's my n. Let's check that this thing is actually exact. So I'm going to go ahead and distribute this. So this is 2e to the 2x plus e to the x y cubed, right? If I just distribute that e to the x. So then the y partial of m is what? So this first term only depends on x, so the y partial of that's 0. Y partial of e to the x y cubed is 3y squared e to the x. The x partial of n is 3y squared e to the x. Oh, Seems almost obvious now that that was the right choice, right? Now, of course, the row is going to be more and more complicated depending on the problem. It is not always possible to solve this in such a way that it works, where row only depends on a single variable. And in general, it's not always possible to do this process anyway. It's just possible a lot of the time. Okay, and it's possible 100% of the time in this course where, this is exactly the sort of thing you're being tested on. Okay, so how does this go? Well, let's see here. Now we have an equation that is exact, so we fall back on the exact same thing that we were doing previously. Okay, so now I want to, thus I seek h of xy such that the x partial of h is equal to m. All right, it's equal to 2e to the 2x plus e to the xy cubed. And the y partial of h is equal to 3y squared e to the x. So this is the system that I'm looking at. The second equation is easier, so I'm going to start here. I'm going to integrate both sides with respect to y, so I get that h of xy is equal to, the integral of this thing with respect to y is y cubed e to the x. This is y cubed e to the x plus, I integrated with respect to y, so the most generic constant of integration here is a constant, or is a function of x. You can just quickly check that if you take the derivative with respect to y of this thing, what you get is 3y squared e to the x plus 0, right? Which is exactly that thing. All right, so now I plug it into this other equation here. So I do the thing I always do. 2e to the 2x plus e to the x y cubed is equal to the y partial of h, the x partial of h, which now I compute here from this h that I found. So the x partial of h is y cubed e to the x plus h prime of x. Okay. So now, once I get to this step, right, I'm done except for finding this little h. So that's really all that's left here. Well, these two terms cancel, and what I'm left with is little h prime of x is equal to 2e to the 2x. Okay. Well, if I integrate both sides now with respect to x, what do I get? Little h of x is equal to integral of this, let's see, so this is, integral of 2e to the 2x. So I have a 2 dx, and that's exactly what I'd have here with substitution. So this is actually e to the 2x, right? So an implicit general solution, which is exactly the thing I was originally seeking here, to our original equation is given by h of xy is equal to constant, i.e. Y cubed e to the x plus e to the 2x is equal to constant. Okay. So this is an implicit general solution for the very original equation that I wrote up before I had found an integrating factor, this thing. Right. Okay. All right. All right, let's do one more example of finding an integrating factor. So yeah, let's do one more. So find an implicit general solution to the equation 4xy plus 3y cubed dx plus x squared plus 3xy squared dy is equal to 0. Okay. Alright, so this is what I want to solve. So I do what I always do here. First, I check exactness. Right, so there's my m, there's my n, and I check exactness here. So this is compute the y partial of m. That is, so y partial of 4xy is 4x plus y partial of 3y cubed is 9y squared. Okay, the x partial of n is 2x plus 3y squared. So man, don't you wish you could just say, well, if I multiply this thing by 2 and I multiply this thing by 3, then I'm happy, right? Unfortunately, these things are not equal. So, not exact. Okay. Alright. So, what do I do? Well, thus I seek rho of xy such that, so I seek rho of xy such that I force this thing to be exact once I multiply by rho. So I want a rho such that the y partial of rho m is equal to the x partial of rho n. Right? Okay. Okay. So let's do exactly the thing we always do. Let's write out this using product rule. So this is the y partial of rho times m plus rho times the y partial of m, and that's equal to the x partial of rho times n plus rho times the x partial of n. So let's see here. What do I want to do now? Well, it's not super clear, right? Because here m and n are like roughly kind of sort of the same level of nastiness. So, well, how can I sort of figure out which way I should go here? So, when you're stuck in a situation where m and n are like the same level of nastiness, you're not sure whether to assume that rho is a function of x or y solely. It can be good to actually write out the expression here to see if there's anything in the algebra that suggests what you should do. Okay, sometimes, of course, you could be in a situation where there's just nothing and you just have to try something. But let's write this out and see how this goes. So I know what m is. It's this thing. So this is 4xy plus 3y cubed, right, times the y partial of rho. Okay. Plus rho times the y partial of m, which we've already computed is this thing. So this would be the y partial of m is 4x plus 9y squared, and this is the this is times the this is just times rho, right? Okay. All right. And that is equal to what? Well, this is equal to the x partial of rho times n. So the x partial of rho is something, I don't know what that is. So n is x squared plus 3xy squared times the x partial of rho. Plus rho times the x partial of n, which I've also already computed. So this is 2x plus 3y squared. And that's times rho. Let's see here. Well, what things would be made easier here? Well, it's not maybe immediately obvious, but here, these two terms share kind of a convenient common factor here, right? Like, so I can factor out, so this 2x, once I rewrite these things here, right, I can notice that, for instance, this, if I factor out an x here, this leaves me with x plus 3y squared, right? Here, so that I would have x times 3y squared here. And that looks like this is going to cancel nicely. Like in the simplification, maybe I'm going to be able to divide out by a single thing here and be okay. So maybe what I'll do is just assume that this thing is 0 here, since I'm left with two terms that I think I can maybe deal with a little bit more. And we'll see how that goes. Maybe that's not the way to do it, and we'll do it the other way if we come to a roadblock here. So let's assume that the y partial of rho is equal to 0. Okay, but you see how this choice becomes a little bit more sticky here. Okay, so what do I do? Well, if this thing is going to be 0, right, then what I'm left with ultimately is 4. So I'm going to be left with 4x plus 3y squared. So this is 4x, or sorry, yeah, 4x plus 9y squared rho is equal to so this 4x plus 9y squared rho is equal to x squared, or I'll go ahead and factor out the actual, so let's write this as x times, oh, I see. So if I pull an x out here, this is x plus 3y squared here. Okay, this, did I do this correctly? Where's my 2x plus 3y squared here? Yeah, so I wanted to leave this term so that I have 2x plus 3y squared left here, and 2x plus 3y squared on the other side. This is, no, this is actually not going to work. Is this going to work the way that I want it to? So let me make sure that I actually did this algebra correctly. Let's see here. 4x plus 9y squared, okay. 2x plus 3y squared, fine. 4xy plus 3y cubed, yep, x squared plus 3xy squared, okay. So then, what am I left with here? So here I have x times x plus 3y squared times the x partial of rho plus 2x plus 3y squared rho. If I rewrite this as like 4 times x plus 9/4 3 squared, and I rewrite this as, so if I rewrite this as 4 times x plus 9/4, which is 3/2 y squared rho, and this is equal to x times x plus 3y squared times the x partial rho plus here, this would be like 2 times x plus 3/2 y squared rho. Okay. So then subtracting these things, right, what do I get? I get x, or I get 2 times x plus 3/2 y squared rho is equal to x times x and is that 2 rho is equal to, yeah, so this would be x plus 3/2 y squared times the x partial of rho. And so what am I left with ultimately, since these cancel, I'm left with 2 rho is equal to x, so that's a 2, not a del, maybe I should rewrite that. So this is 2 rho is equal to x times the x partial of rho. That still looks like a del. I'm sorry, that's just how my 2's look. Okay. So what do I get as a solution to this? Well, this is the differential equation. If you like, x rho prime, right, minus 2 rho is equal to 0. Okay. So x rho prime minus 2 rho is equal to 0. Let's put this into standard or linear normal form if you like. So this is rho prime minus 2 over x rho is equal to 0. Okay. All right. So how do I do this, right? I follow my recipe, right? So that rho of x is equal to, you know, the completely general recipe is like c e to the minus big A of x here, right? Where if I put this in linear normal form, right, this is, so how do I know that it's this, right? It's because this thing is 0. Because this term is 0 when I integrate, so the right-hand side, the little f of x in this case, is 0. And so, here's my completely general recipe is e to the minus big A of x times the integral of e to the big A of x f of x dx plus c times e to the minus big A of x, right? This is my complete recipe for a first order linear equation in this case, but the little f of x is 0 here, right? So little f of x is 0, so this term is 0. C times e to the minus big A of x, what is that? Well, big A of x in this case, this is the integral of minus 2 over x dx. What's the integral of minus 2 over x dx? This is minus 2 times the log of x, right? So this is minus 2 times log x. So then rho x is, c e to the minus 2, so this is 2 log x. Let's use log rule. So this is c e to the log x squared. So this is c times x squared. And of course, I just choose c equals 1 here because I don't care. So rho of x is equal to x squared should work if we go back and multiply it by the equation we started with. Okay, so then here's the equation that we started with. So if I multiply the equation here by x squared, here by x squared, what do I get? So I get that 4xy plus 3y cubed times x squared dx plus x squared plus 3xy squared times x squared dy is equal to 0. So then this thing should be exact. Well, let's just check. So here's my m and here's my n. So if I've done this properly, this should be exact. Let's make our lives easier by expanding this thing. So m here is, I'll just go ahead and write it. M is 4x cubed y plus 3x squared y cubed. And n is x to the 4th plus 3x cubed y squared. So let's check here. What is the y partial of m? Well, this is 4x cubed. So 4x cubed plus 9x squared y squared. And the x partial of n is 4x cubed plus 9x squared y squared. Okay. All right. So this is in fact exact, and now we can go back to doing the exactness stuff that we were doing before we learned about this integrating factor stuff. And so, just to remind myself, here are my equations. So I seek h of x, y such that I seek h of x, y such that the x partial of h is equal to 4x cubed y plus 3x squared y cubed. And the y partial of h is equal to x to the 4th plus 3x cubed y squared. Okay. Now I can pick any of these that I want to. I'm going to pick the second one just because. So I'm going to pick the second one. So then integrating with respect to y, what do I find? H of xy is equal to x to the 4th y plus, integrating this thing with respect to y, I'm going to get a 1/3 y cubed showing up here. It's going to cancel out the 3. So this is plus x cubed y cubed plus, I'm integrating with respect to y, so my most general constant of integration would be a function of x, little h of x. So I'm almost done. I just got to figure out what this thing is, right? To do that, I plug into the other equation like I always do. So 4x cubed y plus 3x squared y cubed is equal to the x partial of h. But from this thing that I found, I compute the x partial. So the partial derivative of x to the fourth y with respect to x is 4x cubed y plus the partial derivative of x cubed y cubed with respect to x is 3x squared y cubed plus the x partial of little h is the full derivative of little h with respect to x. Okay. Now again, since all these are mixed terms, all of them should cancel if everything I did was correct. So 4x cubed y, 4x cubed y, yes. 3x squared y cubed, 3x squared y cubed, yes. Right? The evidence is piling up that we did this correctly. So h prime of x is equal to 0. Okay. All right. So there we go. Okay, so what does this mean? This means that little h of x is actually just a constant. Of course, we don't care what constant we're looking for, an implicit solution, so we can pick that to be 0 if you like, or you can say, well, I just absorbed that in the constant on the right-hand side. Thus, an implicit general solution to our original equation, which I might remind you, looks like this. Is h of xy is equal to constant, i.e. x to the fourth y plus x cubed y cubed is equal to constant. All right, so you saw how involved of a process that is, right? So that took us quite a while to do that, and so these problems are they tend to be very involved, and it's not very surprising because they involve, not only are they at least the length of a normal exactness problem because they contain an exactness problem in them, right? But also they toss in a first order linear problem, which could be as nasty as a completely general first order linear equation. Okay, so that's just how these things are. This is the most involved thing you could be asked to do with these things. Okay, so now kind of a quick review. So this is what we just did is kind of the most involved thing in chapter 1. But a quick review. So what have we done here, right? So there's the basic terminology. Basic terminology involves things like linear versus nonlinear. So linear versus nonlinear, IVP, right? What it means to talk about an initial condition, intervals of definition, separable equations, order of an equation, okay, which is something you won't forget because the course is divided up based on the order of equations. So all of this chapter 1 stuff, so this is all chapter 1 material. All this chapter 1 stuff, that only applies to first order equations, right? When we move to chapter 2, the thing that will distinguish chapter 2 is that we'll be doing higher order equation stuff. So your first homework was due last night. I'm going to post another homework, your second homework, tonight. That will be due in a couple of days. That's going to finish out the rest of the chapter. So there's the basic terminology stuff, and this isn't an exhaustive list, but it's just kind of all the stuff that we've accrued over chapter 1. So secondly, there's linear equations. Linear equations, of course, can be brought into the form. So this is linear normal form. Once they're brought into this form, if big A of t is the integral of little a of t dt, then our closed form solution, there's a recipe for it, right? It's just e to the minus big A of t times the integral of e to the big A of t f of t dt plus c times e to the minus big A of t, right? There it is. So if you have a linear equation in front of you, you can immediately write out the solution to it. The only thing that is required is you have to be able to compute two integrals. You have to be able to compute this one, and you have to be able to compute this one. Right? If you can do that, you can write out closed form expression for an explicit solution immediately. Okay, separable equations. So separable equations look like this. So the variables t and y can be separated, right? So that's why they're called separable. Similarly, boiling down like how to solve this also relies on solving two integrals, but finding an explicit solution would rely on you finding an inverse to one of these resulting integral things, and that could be a little bit trickier. Notice separable equations are not necessarily linear. Linear equations are not necessarily separable. There's overlap, so some linear equations are separable. Some separable equations are linear, but they definitely contain parts, they contain equations that don't belong to the other one. So these are two different things. And a recurring theme in this course is that when you are given a problem, you're not going to be told what to do. You're just going to be told solve, okay? So you're just going to be told solve differential equation and told nothing else, okay, generally. So because of that, it is important that you be able to look at the equation and identify what kind of equation it is, so you know that what it is that you're supposed to be doing. Some people might not like to describe it like this, but you can think of this course at its basic level, right? If we forget some of the conceptual stuff that we leave out, in terms of raw computation and like mechanical understanding, what is going on here is this is basically a flow chart. Okay, so the course is pretty much a flow chart. It is you identify what type of equation you're dealing with, and then you follow the process that we have outlined previously to deal with that. So later in the course, this is going to be, you're going to ask, what order is it? Is it first order? Okay, then I do first order stuff. Is it second order? Then I do some other stuff. And then there's other, there's cases and subcases. So in the case of first order equations, you're not going to ask, like, is it first order? It's going to be obvious. And you're going to say, okay, well, now what do I do? Is it linear? Is it separable? Is it an exact differential form? Is that thing exact, or do I need to use an integrating factor? These are all examples of things that you would ask. So a separable equation looks like this. You can put it into separated differential form, which has it looking like this. This highly suggests wanting to integrate, and you proceed like that. Okay. So the difficulty of that depends very strongly on how complicated this little f and little g are. Okay. So that's separable equations. 4, there's some general theory stuff. The most important stuff from general theory is existence and uniqueness theorem. So this says exactly what we kind of felt before we knew this, that when you have a differential equation, if the right-hand side is nice, and here we're talking about a much more general differential equation, so just dy dt is equal to some big F, right? So we're in the more completely general first order case. So that this could be pretty nasty, but as long as it is like continuous and continuously differentiable with respect to y, so it's not, it's what it does to the unknown function is not too nasty. Then this has the IVP, right, associated to this. So this thing has a unique solution. So it has a solution, and that solution's unique. The most important thing to get from this kind of like immediately, and what we talked about immediately, was when you go to plot out a bunch of different solutions to the same differential equation, this existence and uniqueness theorem tells you that when you plot out trajectories that are plots of solutions, they would have to look something like this. Right? Now, I mean, they don't have to exactly look like this curve, of course. They could look like all kinds of stuff. But their behavior has to be something like this. They're not allowed to cross or touch. And the reason why they're not allowed to cross or touch has to do with the uniqueness part of this. So this existence and uniqueness theorem, it might seem like something that doesn't get applied very much in this course, but it's lurking in the background. And it's the reason why all the pictures in this course look the way they do. Okay? So it's kind of the reason, it is the explanation for why we have the pictures looking the way they do. Okay. All right. So next, I have application or maybe I should say graphical methods, which at this point means phase portraits and asymptotic behavior. So this includes identifying stationary points and classifying their stability. So we have done all of that now, right? We have done several examples of classifying stability of stationary points for some autonomous equation. So maybe that's something to keep in mind. So we did this for autonomous equations, which are a special case of separable. Okay. The nice thing about this is that, of course, we could apply this analysis to things that were very much nonlinear. Okay, so that's one nice thing. And of course, all these methods did not rely on us being able to actually solve the differential equation. So that was also good. All right. So stationary points, classifying their stability. So go back and watch the lecture video on that if you're if you need to brush up on it. It will be, I'm going to give you a homework problem on it soon. So in your next homework that I give you all tonight, there will be a problem on this. Okay. All right. Okay. Next, applications. So these were tank problems. So as I said, once you've kind of seen one, you've seen them all. I think I worked through exactly one example. There's another example right after it in the textbook or in the notes you can have a look at. So these tank problems are, basically once you figure out how to set them up, solving them is just solving a first order linear equation. So they're going to work out to be linear. The main unifying principle here that's used to set up these equations, you have some quantity that's changing with respect to time, and you set up the differential equation, which is the rate of change of that quantity is rate in minus rate out. By far the most important thing, I think, in these problems is to draw your tank, the parameters describing the tank, describe your inflow and outflow. From this picture, you should be able to set up this differential equation and be good to go. The purpose of these questions is not to test like your physical unit knowledge, so I'm not going to try to confuse you with using some crazy units or anything. So so everything will be very straightforward when it comes to that stuff. Okay. All right. Okay, so next, numerical methods, which for us at this point in time really means Euler's method. So in that same section, there's mention of Runge-Kutta and like some other numerical things for first orders, but we're not really going to focus too much on that. All right, so Euler's method's the most important thing. This, if I had a differential equation set up in this very general way, the way to remember Euler's method is that the n plus first time step, or the solution at the n plus first time step, is approximated by solution at previous time step plus h, which is the size of the step, it's step size, times f of Tn Yn. All right. Knowing this alone allows you to implement the thing. Of course, the thing, how you define, so y sub m plus 1 is defined to be y of t sub m plus 1, and t sub m plus 1 is t sub n plus step size h. So you can generate this whole thing recursively in this way. All right. We saw that if you're asked to actually do this by hand, the calculations are not going to be too rough, because this is really meant to be implemented by computer, and you'll do that. You'll implement Euler's method later in one of the MATLAB assignments. Okay, and then lastly, exact differential forms. So you have these equations that look like this. All right, and as we've seen, as I've hopefully been beating into your heads over the last two lectures, there's the first thing you do, which is check exactness. All right, so check exactness. So exactness says that the y partial of m must be equal to the x partial of n. If this is the case, you proceed, right? You seek h such that the x partial of h is equal to m and the y partial of h is equal to n. If that's not the case, then we do this integrating factor stuff, right? So that integrating factor stuff is designed, and I'm not going to write that stuff out again. You can just rewind this lecture to see how that goes. But this is the point. This is how this is how this proceeds, right? If you find that your equation is not exact, you search for an integrating factor. In this course, you'll always be able to find one. In general, you're not always going to be able to find one. But yeah, in this course, for the purposes of this course, you're always going to be able to find such an integrating factor. And then that integrating factor, once you've found it, which typically is going to require solving a first order linear equation, so maybe by the recipe if necessary. So that's how you get your integrating factor rho. Once you've done that, you now have an exact differential form, and you go back and repeat this process outlined here. Okay. Now, of course, at the end of the day, you end up with an implicit general solution. H of xy is equal to constant. Okay. There's a reason why we use this letter h. In certain instances, this h is described as a Hamiltonian. If you've ever heard that word. So this is very important in physics. We're going to see explicit examples of Hamiltonians later in the course. This will be like some of the last things that we do in the course. All right. So that is that. That's kind of an overview of what we did in Chapter 1. So so that's the deal. That's Chapter 1. So tomorrow I'm going to hold a review session. / office hours right after class. So starting at like 12:20, and it'll last about an hour. It'll last like 1:20. and it basically is designed for you to ask, any questions you have about Chapter 1 stuff. And tomorrow I'm going to start the basics of Chapter 2, which is second order equations. So we're moving on. You'll have a homework posted tomorrow. You may have one more homework after that. Maybe not, since you'll have another homework maybe posted on Friday after that. So you should have two homeworks assigned this week. One will be due later in the week. One will be due next Monday. All right. So anyway, that's the plan. So I will see you all later. See you all tomorrow.